Okay.
So thank you everyone for joining, and thank you Tianmin for participating. So Tianmin is a postdoctoral researcher at MIT in the Department of Brain and Cognitive Science, working with Joshua Tenenbaum, and he received his Ph.D. degree from University of California, Los Angeles in 2019. I discovered his work when I was looking for recent publications mentioning either simul movies, so 2D animations, and he did great work on the interaction of language and vision about these animations. So I let you present us your work, Tianmin. Thank you again.
Thanks. It seems that my slide is still loading.
Est-ce que vous pouvez vous taire, s'il vous plaît? Hey! Hey!
Okay. All right. Thanks so much for inviting me here. So today I'm going to talk about our recent work on benchmarking machine social intelligence. Particularly, we are going to present two challenges that are inspired by social cognition studies for humans. So humans are social animals living in a physical world. We can easily recognize social interactions of others in the physical world. We can also actively engage in all kinds of social interactions with others in the physical world. So and we develop this kind of remarkable social intelligence from a very young age. So here is a video where you can see a dog trying to put something into a cabinet, but it doesn't have it cannot really open up the cabinet. And then these very young children actually see these actions and can recognize the adult's intention correctly and figure out what's the best way to help these adults. Even though this kid has never seen this adult before or these kind of similar interactions before. So how we can build up this kind of strong social intelligence for machines? Well, there are a lot of things we need to develop for machines, but in particular, in this talk, I'm going to focus on two aspects. The first aspect is social perception. So basically, the ability to infer mental states, including goals, beliefs, and desires of others from observed actions of other people. And in the past, people have been trying to study this by building computational models for theory of mind. Basically, the kind of model that can infer mental states from observed actions. But people have been only focused on very simple domains like these 2D agreeable domains where you have these dots moving around in a 2D maze and trying to infer the intention, belief, and desires of these dots. The second aspect is human AI collaborations. So particularly, we're focusing on the aspect of planning and learning to help. And in this direction, people have been working on some multi-agent games where you have these characters trying to, for example, on the left cases, trying to cook something together. Or you can have a robot trying to help a human. But usually, in this case, people use this lab environment. So it's in the real world, but it's very limited. You only have 1 or 2 settings in the same lab. In the first part of talk, I'm going to present a data set we developed that aim for benchmarking machine social perception. And particularly, we are focusing on this physically grounded abstract social event. I'm going to talk about what it means. In this particular work, we are interested in building models that can recognize social interactions under different kind of physical constraints. So consider the example, the image on the left. You have 2 people carrying the box, and they are carrying one box by themselves. And you can infer they can do this because, first of all, they want to work on moving something together, right? And second of all, the box are probably very light, and then they are strong enough to carry one box by themselves. On the other hand, you can see 2 people carrying the same box together. So the kind of social interaction is very similar to the left-hand side, but the action you observe is very different. And it's only because the physical constraint now changes. It's not two light boxes, it's one single heavy box, so they have to work together. So in this, so basically we want to capture this kind of richness in the of the social interactions in different kind of physical environments by a synthetic data set. So we build a data set which we call face. We provide some state-of-art models as baselines, and we suggest a different model that can outperform the state-of-art models. So in the past, people have been trying to build convolutional data sets for understanding social interactions, but they are only focusing on very simple scenarios, like a group of people crossing the street, a group of people waiting together, or two people hugging, high-fiving, kissing, etc. These are real videos, but the social interactions captured in these kind of videos are very simple. You don't have concepts like helping, hindering, collaborating, competing, etc. But those concepts are actually very common in real life. On the other hand, people actually can infer very complex social interactions from very simple stimuli. So here I'm showing an example of a very well-known animation called hide and symbol animation or hide and symbol movie. So in this kind of animation, you only see the movements of some simple geometry shapes. But if you show this kind of movie to a person, that person can actually tell you a very vivid story about three people. So they can recognize very complex real-life social interactions even from these very simple videos. So inspired by this, instead of spending a lot of effort to collect real human interactions, which could be very, very difficult, we actually try to generate hide and symbol type of simple animations that can resemble a wide range of complex real-life social interactions. So how can we do this? Let's imagine that we try to generate animation that resemble this case, basically two people carrying a heavy box together to some place. So what are the critical elements we have to replicate in the animation? Well, first of all, you have two agents having some goals. So basically, in this case, two agents will have a goal, which is working together to moving this box to some place, right? So in that case, you also have objects, some kind of locations, and you also have some kind of obstacles like walls. So if you want to move one box to from one room to another room, you cannot go past the walls. Given this situation, you also have relationship between these two agents. And in particular, in this case, you have two friends, and you also have some kind of social interaction between these two agents, which is in this case, one friend helping another friend. And in order to do this, both of you should do something together. So in this case, you need to carry the box together, lifting the box, in order to avoid some bad outcomes like dropping the box. So for replicate these kind of social interactions, we come up with this setup, this 2D animation setup, where you have two agents, you have several objects, you have some locations of interest, which could be your target location. You have walls which you cannot pass through, and then you have the so agents have limited field of view, so you can only see something in front of you, and agents can apply actions. So in this case, an agent can exert force to yourself so that you can move. The agents can grab some objects, and agents can also release objects at some point. Agents also have different strengths. So here the strength is defined by the maximum amount of force you can apply to yourself. A weaker agent cannot move a very heavy object. In this case, you need to have two agents work together. Is that clear? Okay, so agents have some physical goals, and a physical goal could be putting some object to some landmark, or it could be approaching another agent. It could also be going to some landmark by itself. Agents also have different relationships, and depending on your relationship, you can have different social goals. So, for example, if you are friendly towards another agent, sometimes you may try to help that agent. Or if you are just neutral with another agent, then the two agents will just do their own things separately. However, sometimes they may bump into other, so that they may accidentally interfere or aid each other, but that's not going to be intentional interactions. But sometimes you can be enemies, so you can have an adversarial relationship. In that case, you can compete with another agent or try to hinder another agent. So we come up with this framework to procedurally generate a large set of videos automatically using this simulation. So we will first sample some physical and social configurations, pass this configuration to a simulator, and let the simulator to generate a video. So how we can do this? So first of all, we are going to sample some physical configurations. That includes the size and strength of the agents and all the objects, the room layout, and the initial states. So that includes the initial positions and orientations of all these entities. And we put this into a physics engine so we can recreate these 2D environments where objects and agents are physical bodies in this physical engine. Then we'll get some observations for the agents, and we pass this observation to each agent. We also assign social configurations, including the goals and the relationships between the two agents. And given the social configurations, the agent can then decide what's the best actions to take based on the according to the current observation. And then they will give these pass these actions into a physics engine to and we'll apply the force corresponding to this action and simulate one step in the physics engine. After the simulation, we'll get updated observation for each agent, and their planner will tell the agent what's the best thing to do next. So here the planner could be an actual human player to control these agents. We actually have a game interface where two agents can play this game, each controlling one agent to achieve some goal. But it could also be controlled by a algorithm. So specifically, we come up with this hierarchical planning to control agents by a machine model. I'm not going to talk about the details here, but I'm happy to go into details if you are interested in after the talk. So then we have these two ways to control the agents. One would be agent will be controlled by two human players. The other will be agent will be controlled by this hierarchical planning model. And we compare these two kind of approach together. So this is an example where these two videos have the exact same physical and social configurations. So they should represent the same social interactions. And indeed, that the generative model, generative videos by different approach actually look very similar. In fact, we actually generate 100 human videos and 100 machine videos, and we show these 200 videos together to subjects and let them to rate how likely human will behave in the same way if they have the same social same goals and relationships. So basically, we ask people to rate the human likelihood of these videos, and then and also they don't know how the video are generated. So it's in some way like a tuning test. And then if you look at the average ratings for human control videos and for machine control videos, they're actually essentially the same. So so this actually suggests that our hierarchical planning model actually can capture the human plans very well. And because it has an additional benefit, which basically means that we can do this automatically without having human involved, then we are going to focus on the machine control method to generate a larger set of the data sets. And in particular, we now have generated 500 videos, but we are planning to generate more in the future. So we show this. One question we want to ask is that are these models actually resembling? Are these videos are actually resembling real-life social interactions? So to answer these questions, we show 20% of the generated videos to human subjects and ask them to rate, ask them to assign some simple phrases to describe these videos. And in the end, we collect, we get like 18 categories from human subjects. And for example, you can get something like tracing, run away, start, approach, avoid, block, fight, compete, help, collaborate, etc. And this actually really validates our hypothesis that by simulating these abstract social events, you can actually generate something resemble real-life social interactions. And there's a large variety among these interactions. Okay, so with these kind of videos, we designed two tests, two social perception tests. The first test would be recognition. So we can show a video like this to a model and ask the model to recognize the goals of all the agents and also the relationship between the two agents. We can also show part of the video, like for example, we can show the first part of the video here and ask the model to predict the next 2.5 seconds. So the future trajectory of these agents. So how the model works. So one type of model that is the most common, basically the most common framework in the state-of-the-art models in computer vision is this kind of one-by-one mapping model or bottom-up model. Basically, they observe some kind of trajectories and directly map it to goal and relationship for recognition, or directly map it to some possible future trajectories for prediction tests. And specifically, there are two types of state-of-the-art models that people nowadays use. So one would be based on LSTM, which is a type of recurrent neural net, plus some kind of social pooling. So the basic idea is that they're gonna represent each agent by LSTM to get some feature for the agent, and then they're gonna pull over all the outputs from each individual LSTM to get the context or the interactions among these agents. And you can use that to recognize the interactions or the relationship between different agents. The second type of model is a little bit more advanced. So basically, people can build a graph for these agents. So each node will be a agent, and the edge will represent the interactions or the social relationship between two agents. And then you can use these nodes and edge to recognize the goals or the relationship between the agents. Similarly, for predictions, people are also using these two types of models. You can use LSTM model with some kind of social pooling to predict individual trajectories, the future trajectories of individual agents. You can also use graph neural nets to do the same thing. However, this is not sufficient according to prior studies of human cognition. So it has been shown in psychology that people are actually doing more than that. They are doing some kind of mental simulation to verify the hypothesis they come up with to interpret some videos. So to inspired by this kind of study from human cognition, we build this different model. We call it simple. So basically inference by simulation, planning, and local estimation. So what it does is that, first of all, you'll do something very like the current model. So using some kind of bottom-up proposal to directly guess what could be the best goal and relationships and strengths of these agents based on the trajectories directly. So here the Q-based proposal could be one of the neural nets that we just see a moment ago. Now, instead of just using this output from neural net, we can input this hypothesis for the goal and relationship to the same simulator that we use to generate the videos, and then we're gonna, so we can in that case simulate what could happen if their goals and relationships are indeed these indeed the same as the hypothesis, right? And then we can compare these synthesized videos with the actual video we observe. So of course, in this case, we can see that there's some kind of errors in part of the video. So next, we're going to focus on the part where we have this very large error and propose a new hypothesis. That will be basically the hypothesis in the next iteration. And then we're going to do the same thing. So we're based on the new hypothesis, we can generate new videos and compare the new videos with the actual video, and we can get this error. And we're going to use the error to update our hypothesis again. So after several iterations, we can converge to some a much better hypothesis about the goals and relationship. So how does all this model work in this benchmark? So the first, we're going to show the accuracy of recognition tests. So first of all, we have a human performing the same test. And you can see that the accuracy of human actually approaching basically 100%, or very close to 100%. And then we have two types of neural net model. One would be LSTM based, one would be graph neural net based. They are all very far away from human performance. Now we show our proposed model, which clearly outperform all these state-of-the-art model, but still there's a little gap between the current model and the human performance. We can also show the prediction errors for the second test. Specifically, people often use two metrics here. So the ADE metric on the left-hand side represents the average displacement error. So they're gonna compare the prediction error between an average prediction error across the whole trajectory. The second metric is FDE, so final displacement error. So they're just gonna compare the final positions of the predicted trajectories with the actual final positions of the actual trajectory and get this error. And we show these two different portions of the videos. So we can show the first 7.5 seconds, or the first 12.5 seconds, or the first 17.5 seconds, and ask the model to predict the next 2.5 seconds. So these kind of settings are actually very typical in the computation literature. And you can see that for the neural net models that we evaluate, even though they are actually the best model in the current literature, they actually have a very large prediction error. Now, if we use our model, the simple model, it actually has a reasonably low error, and more importantly, the error will decrease by using our model when you have more and more observation, which makes sense because when you observe more videos, you're more certain about the Guangqiu's goals and relationship of these agents. Hence, the prediction will be more accurate. But this is not the case for neural nets. So to sum up, we have proposed a data set that combines physical scene understanding and also social scene understanding. This is just a first step towards simulating social interactions. There are a lot of things we can do to improve it. And also the current model are still very limited. So even with the best performing model, the simple model we propose, it still has some downsides. For example, it requires us to use the same simulator that we use for generating the videos, which is not ideal. So the most ideal case would be how we can learn those simulators, like the planning and the physical simulation should also be learned by a model together. And then we have released data set on our website, so you can you're welcome to try it out. Okay. Now we have talked about the first aspect. So for the second part of the talk, I'm going to present a challenge that try to combine these two aspects together. Okay, so in this work, we present this new challenge we call watch and help for combining social perception and human AI collaboration. It's very much inspired by this baby study, but instead have a baby to do this task, we want to have a machine agent to do this task. But it's very hard to have a robot to work in the real world environment. So to do that, we built a virtual environment, which we call virtual home social, where we can put multiple agents in a virtual household platform. Okay. It should be working. The video doesn't play, but doesn't matter. We have more video to show. So basically, we have set up this virtual apartment environment where we have in this challenge we have two agents. So the first agent is the main agent, which has a goal to perform some tasks. So for example, the main agent may try to set up a table. The second agent, which is helper agent, doesn't know the goal of the first agent. So you need to first infer what's the goal of the first agent, and then try to help the first agent to achieve the same goal as fast as possible. And particularly, we have two phases. The first phase is the watch phase, where we're going to show a demonstration of the first agent trying to do some tasks. So it will be something like this. So basically, you can see that the agent puts a plate on the table and puts a glass on the table. So that's the goal of the agent. Now, after watching this video, the helper agent need to infer what is the first agent, what is the goal that the first agent trying to achieve here. And based on that inference, we're gonna have a second phase, which is a help phase. So we'll put main agent, helper agent together in a totally different apartment and ask them to work together to achieve the same goal as fast as possible. So you can see here that the helper agent will achieve part of the goal together with the first agent. So in that case, they can finish the task much faster than just having a single agent to do it. Okay, so ideally we should have a main agent as a human agent, right? Because the goal is to have human AI collaboration, but it's very hard to have a human in the loop training if we want to train some machine agents. So instead we have a building agent, pretend to be a human, and it's implemented by a planning-based agent. So the planning-based agent follows the usual setup of PumpDP. Basically, you have some partial observation of the world. You use that partial observation to update your belief. So basically, belief here is represented by the possible locations of each object in this apartment, right? And then based on the belief and also the desire, which is your goal, you can plan to execute some actions, and then the action will change the world state, which will change your observation, which will in turn change your belief, and you will change your action again. So you will do this over again until you reach the final goal. I'm not going to show the details of the agent, but I can talk more afterwards. Okay, it seems to be freezing now. Let me restart it. Okay, so how we can set up a system for evaluating this kind of a test. So for each episode, we're gonna we'll actually sample a test from a database. So we have actually generated more than 1,000 tests offline, and then each time we're going to sample one test, and the goal of the test is defined by some predicates. So for example, one goal could be put a plate a glass and fork on the table, but it could be a different task could be have different kind of predicates. And based on these tasks, we have corresponding demonstrations of the main agents doing this task in some environment. So that would be the demonstration we show in the watch phase. So in a help stage, we're going to put two agents together in a totally different apartment and allow them to perform the same task. So to connect these two phases, we can do something like this. So we're going to sample a task and then generate the demonstrations. We show the demonstration to a watch model, which will try to predict what's happening here, what's the goal here, and we'll have some kind of predictions. In this case, it's not totally correct, but that's okay. And then in the helping phase, we're going to put two agents together. One will be a building agent, which the model cannot control, but the model can control the helper agent here. So a helper agent will have a help model, which will get the predictions, the predicted goals, and then use that to execute actions to help the building agent here. So there are multiple ways to build a help model. In the baseline that we show here, it inputs the predictions and also the observations and outputs the possible actions for the helping agent. And specifically, we have three types of models here. You can have a hierarchical planning model, which will first generate a high-level plan, basically a sequence of subgoals, and each subgoal is basically a predicate. So, for example, a subgoal here could be first achieve these predicates, so put a glass on table, and second, you can put a plate on table. And then it has a low-level planner, which will figure out what will be the action sequence to achieve each subgoal here. So, for example, to achieve the first subgoal, you can have three actions: walk to the glass, grab the glass, and walk back to the table. And then the final action actually will be put the glass back onto the table, so you can achieve that subgoal. We can have the hybrid model. Basically, for the low-level planner, we use the same low-level planner to figure out what will be the action sequence to achieve each subgoal. But for the high-level planner, it will be replaced by a reinforcement learning policy, which will be used to figure out what will be the best next subgoal to achieve. So the high-level policy will be learned. On the third model, we can learn both the high-level policy and low-level policy together, all using reinforcement learning. And we can evaluate these agents with different kind of metrics. The first will be success rate, and we count the success if all the predicates can be achieved within a time limit. We can also, compute compare the speed up, relative speed up with respect to main agent working alone. So for the same task, we can let the main agent to work alone, and we get the time. And we can also count the number of steps it takes for both of them work together to achieve the task. And we can use the relative speed up to measure the how good the helper agent it is. So in this case, we can evaluate all these models. I'm not going to show the details here because of time limit, but basically the main conclusion here is that the hierarchical planning model works the best. And then the next best, but then also, we also have an interesting baseline here where you have the hierarchical planning model, but it has a random goal. So basically, each time you don't use the inferred goal, you randomly sample a goal to a helper agent to help. But then in that case, it's actually not helping at all. It's actually hurting the main agent, because sometimes you will have this conflicting goal here. So for example, here you have a random goal, which is to put one glass into a dishwasher, but the true goal is actually put the glass on the table. So in the end, we will see actually you have an infinite loop. The helper agent will try to put one glass in the dishwasher, and the main agent will try to put the glass back on the table. So I'm not going to show this here, but I can show later if you're interested. We also so this is like a example of the collaboration. So basically, a system of collaboration will have two agents exploring different parts of the apartment to find objects faster, and they can achieve different parts of the goal simultaneously, so that they can finish the task as fast as possible. I also skip this. the other things like sometimes you can have false belief caused by the actions of one agent, but I also not show it here. Okay, so the final goal of the project is actually try to have real humans, to have an agent to work with real humans. To achieve that, we can ask a real human to control the main agent by this interface, so they can click this button to select action, and then the main agent will execute these actions in the environment. And based on that, we can basically evaluate have a different evaluation. So on the right-hand side, left-hand side, you have planning-based agents controlling the main agent. So in that case, you have machine-machine collaboration. On the right-hand side, you have a human controlling the main agent. So in that case, you have human AI collaboration. And we can use the same procedure to evaluate both machine-machine collaboration and also human-machine collaboration. Okay, so with that, I'm going to conclude my talk. So again, for this project, we also released all the data sets and the code, and you're welcome to try it out. Thank you.
Thank you very much, Tianmin. Is there any question for Tianmin? Maybe I can start with one. You showed that when you have a human agent in the watch and help scenario,
yeah,
you have better performance than with machine-machine interaction.
Oh, that's that's actually an interesting case. So okay, this is the graph. So here we are using this reward to evaluate it. So reward is defined by whether you have successfully reached the goal here and how many steps do you need to reach that goal. So the higher the reward is, the better performance is. So here you can see that all of these baseline, the ranking of these baselines are kind of similar into two conditions, but they are when you have a human involved, it's slightly better, and that's because the human has a better way to adapt to a machine agent actually. Particularly a very interesting case here. So if you see the HPRG baseline, basically this is a baseline where we randomly sample a goal for the helper agent to pretend that's the actual goal of the main agent. In that case, when you have a machine-machine interaction, it's actually very bad. But when you have a human agent interaction, it's actually not that bad. And this is an example here. So let's say we have like a random goal sample for a helper agent, which is actually totally wrong, and it has a conflict with the actual goal here. So you want to actually put the gas on the table rather than put it in the dishwasher, right? But when we have machine-machine interactions, the machine agent actually cannot adapt to this incorrect goal, and then they will just have this infinite loop. So the help agent will put it into the dishwasher, and then the main agent will get it out, and it will just go back and forth. But when you have a real human as the main agent here, it can actually recognize that this incorrect goal inference from the helper agent and avoid conflicts. So here's the example how it looks like. Okay. So first, the helper agent, which is the male agent here, puts the gas into the dishwasher. Okay, so it's totally wrong. So when the main agent, which is the female agent here, when it's controlled by a machine agent, it will actually go to get it out immediately and put it back on the table. But in this case, it's actually controlled by a human. When it's a human, it will just ignore this part and do the rest of the goal first. And when it's finished all the other goal, and then it will actually eventually come back to grab the cup, the gas out of the dishwasher and put it back. So in that case, you can actually finish the whole task instead of getting into like a infinite loop.
Okay, thank you.
Yeah.
And another question I have is about the 2D animation movies. I would think that detecting the goal may be ambiguous in some time because, for example, your goal may be either to help the other agent to put the object in a corner, or yourself to put the object in the corner, and you wouldn't distinguish the two situations easily just by observing the movie. So I
Yes.
wonder if this situation often occurs.
Right. So I think so we're actually extending the current system so we can do something more. So one thing we're adding is the communication, which is very important when you're trying to help someone, right? Especially when you are not really certain about what is the thing I need to help you with. So in that case, when you are uncertain about the true goal, maybe in the process, in the helping process, you can try to communicate with the main agents and ask like, is this something you want? Do you want me to put something here or something there? So something like that. Or maybe the human agent may find out that the machine agent trying to do something wrong, and you can correct that agent by communicating with that machine agent. So that's one way. Another way would be when you try to plan yourself to help the main agent, you need to actually consider this ambiguity. So sometimes, for example, you actually have no idea what this main agent is actually trying to achieve here. So in that case, maybe the best thing for you to help is not to actually put something somewhere specifically, but maybe just to clean up the apartment, like in a tidy way, so that you don't chip over, you don't like block, you don't have something block your way. So when you have this kind of ambiguity built into a planning, you can also have a better helping strategy, even though you are very uncertain about the true goal.
Okay, thank you very much.
Yeah.
Are there any other questions?
I mean, I have a questions, but first of all, thank you for the talk. I can turn on my camera. I guess it's sort of a follow-up on what David just asked you. When you mentioned this definition of working together at the beginning, right?
Yeah.
Sort of typical ideas that it's not just that you know the goal of the other person, right? But that they know that you know that you know that they know, etc.,
Yes.
etc. And sort of, and so I think this is why if I was really interested in this comparison, just like David mentioned, between the human and the sort of the PalmDP, because in a sense, would you be able to simulate the fact that basically or even in the hydrozimal case, when you're optimizing, you're not optimizing considering necessarily that someone else will also be helping, right? So how do you handle this sort of truly joint goals, as opposed to, this idea of, as opposed to having two goals that at, let's say, level 0 coincide, how do you have a truly joint goal where they both know that they do a part of an action, but that this action is also a part of this joint action?
Yes.
I don't know if I'm making myself clear, but
yes,
this is
I
totally
understand that. Yeah. Yes, that is an excellent question. So basically, in the agents in the second work, it doesn't really consider the other agents' actions. I mean the main agent, but the helper agent actually we define here actually will predict what the main agent trying to do next. So in that case, it's actually very important, because sometimes you can try to reach for the same object and you'll have this collision. And if you don't predict that, you'll have basically a lot of these collisions, you won't be able to help actually. In the highly simple case, right now we are having this very simple model of all the other agents. So basically we'll consider, first of all, assume that we know the goal of the other agents in the simulation, and we're gonna predict what the other agent will move in the next step. And then we'll use that kind of prediction to help us to figure out what's the best way to help that agent, or to try to compete with that agent in some cases. But that kind of model is still way too simple. So another direction we are exploring here is that in the future work is that we want to come up with this recursive reasoning. So basically, like that you say, you know what I know, I know I know you know, something like that. And the one kind of difficulty is that it's very complicated and very expensive. So one way we are trying to do here is that can we train some kind of neural nets to help us to do this kind of recursive reasoning faster instead of going to very deep kind of depth and then and try to reason this very complex process.
One of the idea, I mean, I don't know if you consider that, but if you look at it, I mean, on the literature on joint action, is that so comparing to this problem of setting up common ground, common knowledge, is that people actually, you could either do this recursive system, this recursive thinking, but you know that's really costly. So one of the ideas to actually set up a signal that's inherently common knowledge, like I look at you, I do an action, or basically if you communication, doing something in presence of someone else, like pointing while someone is looking at, you can right away ensure that this becomes common ground. So that's the idea of instead of having to use this recursive thinking, signaling essentially would be the way to make sure you right away establish. So if you do the communication case, if I say I'm going to help you, and the person has been listening, and then you already right away have this common setup, as opposed to having to do really without communication, in which case the coordination problems becomes very complicated indeed.
Yes, I totally agree, and that's why we are also exploring the communication part of this, and specifically in a collaboration case, I think it's also important to have like a joint plan in your mind. So you imagine that what's the best distribution of labor among yourself, and then you basically can expect what your partner can do. What's the best action for your partner, and what's the best action for yourself. So if that expression is matched with the reality, then everything is fine. You have established a common ground before, so you can just do it, do your own job. But if that expression is different from what you actually observe from your partner, then maybe you don't have common ground at that time. So you need to maybe use communication to establish that common ground again, so that you can do the same more smoothly. Right. I think it is a very good direction to explore.
Thank you.
Okay, thank you very much. Is there any other question? Okay, if not, thank you again, Tianmin, for your participation. And I invite you all to join next week, where Alexandros Pantazis will talk about his work on a rural community set up in Greece, so around farming tools. So thank you very much, and see you there.
Yeah, thanks. See you.
Thank you.
Bye.